You're sitting on a plane, seatbelt on, waiting for takeoff, and somewhere beneath you, inside the wings stretching out on either side, there are hundreds of thousands of litres of jet fuel, not in a tank in the cargo hold, not stored safely in the centre of the aircraft, but in the wings, those long, thin, constantly flexing structures that bend visibly in turbulence. And if you've never thought to ask why, you're not alone. Most passengers never do, but the answer is one of the most brilliant pieces of engineering in the history of aviation. And once you understand it, you will never look at an airplane wing the same way again. Stay until the end. Because the last point reveals something about wing fuel that most people find genuinely shocking the first time they hear it. 1. The obvious answer is wrong. It's not about space. The first thing most people assume when they hear that fuel is stored in the wings is simple. The wings are big. There's space out there. Why not use it? But that explanation misses everything that actually matters. Commercial aircraft like the Boeing 747 carry up to 238,000 litres of fuel. The Airbus A380 carries even more, up to 320,000 litres. That is an extraordinary amount of liquid weight that needs to go somewhere. And yes, the wings have space. But engineers don't put fuel in the wings because there's room. They put it there because of what that weight does to the aircraft when it's in exactly that position. And understanding that requires understanding one of the most fundamental challenges in aircraft engineering. A challenge that the wing fuel system solves so elegantly that it has been the industry standard for decades. The challenge is stress. Specifically, the stress that flight places on the wings themselves. 2. Every flight is trying to tear the wings off. The fuel stops it. This is the part that changes how everyone sees this. When an aircraft is in flight, the wings generate lift, the upward force that keeps the plane airborne. That lift acts along the entire length of the wing, pushing upward from the wingtips inward toward the fuselage. Meanwhile, the weight of the fuselage, the body of the aircraft, the passengers, the cargo, the engines, pulls downward at the centre. These two forces acting simultaneously create what engineers call a bending moment. The wings want to bend upward at the tips. The fuselage pulls the centre down. The point where they meet, the wing root, where the wing joins the body of the aircraft, experiences enormous stress with every single flight. On a fully loaded commercial aircraft in cruise, the wingtips can flex upward by several meters. You can see this from a window seat. Those wings are not rigid. They're constantly working against enormous forces trying to bend them permanently out of shape. Now here is where the fuel comes in. When fuel is loaded into the wings, its weight acts downward along the entire wingspan, directly opposing the upward lift force, counteracting the bending moment at the wing root. The fuel is not just a passenger in the wing, it is a structural counterweight, actively reducing the stress on one of the most critical components of the entire aircraft. Every litre of fuel in those wings is doing two jobs simultaneously, powering the engines and protecting the structure that keeps the plane in the air. 3. Where the weight sits changes everything about how the plane flies. Here is the second layer of engineering brilliance behind wing fuel storage, and it involves the physics of balance in a way most people never consider. Imagine holding a long, heavy rod at its centre. Now imagine holding the same rod at one end. The second position requires dramatically more effort to keep stable. The weight distributed far from your hand creates leverage that works against you. Aircraft engineers face the same challenge. A plane carries enormous weight: fuel, passengers, cargo, engines. Where that weight is positioned relative to the aircraft's centre of lift determines how much energy is required to keep the plane stable and level. Fuel stored in the wings distributes weight along the wingspan, spread far out from the centre of the aircraft. This creates a natural stabilising effect. It reduces the tendency of the aircraft to pitch, to nose up or nose down during flight. It makes the aircraft more inherently stable and requires less constant correction from the control surfaces. In practical terms, this means less drag, less fuel consumption to maintain level flight, and a smoother experience for everyone on board. And as the fuel burns during the flight, engineers have designed the fuel system to burn from specific tanks in a specific sequence, maintaining the optimal weight distribution throughout the entire journey from takeoff to landing. The fuel management system on a modern commercial aircraft is not just pumping fuel to engines. It is constantly managing the balance of the entire aircraft in real time. 4. The wings solve a problem with jet fuel that almost nobody knows exists. Here is something that surprises almost everyone who hears it for the first time. Jet fuel has a problem with temperature. Specifically, it does not like being too warm. At high temperatures, jet fuel begins to evaporate. It produces vapors, and fuel vapor in a confined space is significantly more dangerous than liquid fuel. It is the vapor, not the liquid, that ignites. Now consider the alternatives to wing storage. Fuel stored in the fuselage, in the belly of the aircraft, sits close to the engines, close to the hydraulic systems, close to the electrical systems, and close to the heat generated by hundreds of passengers over a long flight. But the wings are different. At cruising altitude, the outside temperature is typically around -50 to -60 degrees Celsius. The wings are directly exposed to that cold. The metal of the wing structure acts as a natural heat sink, keeping the fuel significantly cooler than it would be anywhere else on the aircraft. Cooler fuel means less evaporation, less vapor, a dramatically safer fuel storage environment. The wings are not just structurally ideal for fuel storage, they are thermally ideal, the coldest, most naturally temperature-controlled spaces on the entire aircraft. If this is changing how you see the engineering around you, hit the like button and subscribe. We explain the science behind aviation every week in a way that actually makes sense. 5. The most dangerous moment is not a full tank, it's an empty one. Here is the counterintuitive truth about aircraft fuel management that most passengers never consider. A plane with full wings is actually structurally safer than a plane with nearly empty wings. Remember the bending moment problem from earlier, the enormous upward force of lift trying to bend the wings at the root. Full wings counteract that force. The weight of the fuel pushes back against the lift, reducing stress on the wing structure. But as fuel burns and the wings get lighter, that counteracting force reduces. The bending stress at the wing root increases. The wings flex more. The structural loads increase. This is why fuel management sequencing is so precisely engineered. Engineers design the burn sequence to maintain as much fuel as possible in the inboard wing tanks, the tanks closest to the fuselage, for as long as possible, preserving the counterbalancing effect where it matters most, at the wing root, for the maximum duration of the flight. The outer wing tanks burn first, the inner tanks last. Every drop of fuel burned on a commercial flight follows a sequence that was designed not just to feed the engines, but to protect the aircraft structure from the moment of takeoff to the moment of landing. 6. What this engineering really represents. The next time you board a plane and look out the window at that wing, stretching out beside you, flexing slightly in the turbulence, carrying hundreds of thousands of litres of fuel inside its structure, consider what you're actually looking at. Decades of engineering refinement, thousands of hours of stress analysis, the accumulated knowledge of some of the most brilliant minds in aerospace history, all working on the same problem. How do you carry enough fuel to cross an ocean in a structure light enough to fly, safely enough to carry hundreds of people, efficiently enough to make it economically viable? And the answer they arrived at is the wing fuel system. Elegant in its simplicity, extraordinary in its engineering depth, it solves the structural stress problem, it solves the weight distribution problem, it solves the temperature problem, it manages the balance of the aircraft in real time throughout the entire flight. One solution, 4 problems solved simultaneously. That is not just good engineering. That is the kind of thinking that turned a 500-ton machine into something that leaves the ground every day as if gravity is merely a suggestion.